Bismillah ar-Rahman ar-Rahim. Dear students, welcome to the course of Nuclear Chemistry, Chem 416. Today, first we are going to solve some numericals on binding energy, and then we will discuss the packing fraction and the packing fraction curve, and then I will talk about the nuclear forces. At the end, I will summarize the whole discussion. So first, let's solve some numericals on binding energy. Question 1. Calculate the binding energy per nucleon for oxygen 16, whose actual mass is 15.99492 AMU. Now we know that oxygen contains 8 protons and 8 neutrons. So by using this information along with the mass of proton and mass of neutron value in AMU, we can calculate the expected mass of nucleus by adding up the masses of 8 protons and 8 neutrons, and then we subtract the actual mass of the nucleus from the calculated mass, and the answer which we get is 0.13701 AMU. Now we can convert this mass defect into energy by simply multiplying it with 931.5 MeV per AMU, and the answer which we get is 127.619 MeV. This value can be converted to binding energy per nucleon if we divide it by the nucleon number. In this case, the nucleon number is 16. So 127.619 divided by 16 is equal to 7.98. So the binding energy per nucleon for oxygen is 7.98 MeV per nucleon. Question 2. Calculate the binding energy of uranium-235 in kilojoules per mole. Uranium-235 has 92 protons, 143 neutrons, and has an observed mass of 235.04393 AMU. So first we will calculate the mass defect in AMU, and for this we will multiply the proton number with the mass of proton and the neutron number with the mass of neutron, and then we will add up these values. The actual mass of uranium is then subtracted from this calculated mass, and the answer which we get is 1.86564 AMU. In the second step, we will convert the mass in AMU to kilogram by simply multiplying the mass in AMU with 1.66 times 10 to minus 27 kilograms per AMU, and the answer which we get is 3.09797 times 10 to minus 27 kilograms. In step 3, we convert this mass in kilograms to energy in joules by using the Einstein's equation. So we multiply the mass in kilograms with the velocity of light squared, and the answer which we get is 2.7843 times 10 to minus 10 joules. This value in joules can be converted to kilojoules per mole by multiplying it with Avogadro number and dividing it by 1000. The answer which we get is 1.6762 times 10 to 11 kilojoules per mole. So the binding energy of uranium-235 isotope in kilojoules per mole is 1.6762 times 10 to 11. Question 3. Calculate the amount of energy released when uranium-235 undergo fission and form cesium-141 and rubidium-93. Binding energy per nucleon values for uranium-235, cesium-141 and rubidium-93 are 7.6, 8.35 and 8.7 mega electron volts respectively. So first we will calculate the binding energies of these three nuclides by multiplying their nucleon number with the respective binding energy per nucleon. So in case of uranium, we get the value 1786 mega electron volts. In case of cesium-141, we multiply the nucleon number 141 with the binding energy per nucleon value 8.35, and the answer which we get is 1177 mega electron volts. When a similar type of calculation is performed for rubidium-93, the answer which we get is 809 mega electron volts. Then we can calculate the energy released by using this formula. Energy released is equal to sum of binding energies of products minus sum of binding energies of reactants. And when we substitute the values in this formula, then the energy released is equal to 200 mega electron volts. So when a uranium-235 nucleus undergo fission and form cesium-141 and rubidium-93, then about 200 mega electron volt energy is released. Now let's see what is meant by this term packing fraction. This term was introduced by Austin, and he used it to compare the stability of various atoms. Packing fraction is the ratio of difference of actual isotopic mass and mass number to the mass number multiplied by 10,000. And it is the ratio between mass defect and the mass number. Or simply I can say that it is mass defect per nucleon and can be used to assess the comparative stability of nuclides. Now mathematically, packing fraction PF, or simply F, is equal to isotopic mass minus mass number divided by mass number. And since this value is very small, so in order to make it significant, this ratio is multiplied by 10,000. Now this formula can be written in different forms. For example, it can be written in this form: m is equal to f plus 1 multiplied by A divided by 10,000. So let's calculate the packing fraction of chlorine 35 isotope, and for this we will need the actual mass of chlorine 35 isotope, that is 34.980 AMU. So when we substitute values in this formula, the answer which we get is minus 5.7. Now this is a portion taken from a paper published by F.W. Austin in 1927 in the journal Nature. And in this table he has calculated the packing fractions of various nuclides, and he has taken the mass of oxygen 16 as the standard. Therefore, for oxygen he is getting a value of 0 for the packing fraction, and fluorine is monoisotopic, so again the packing fraction value is 0. And you can see that majority of the nuclides, they have negative packing fraction values. Some of the nuclei, they have positive packing fraction values. Now packing fraction curve. Packing fraction curve is a graph of packing fraction of nuclides versus their mass number. And the packing fraction can have positive values, or packing fraction can have a 0 value, or packing fraction can have minus values, as was also seen in the table published by Austin. The 0 packing fraction value is found in monoisotopic elements, where the isotopic mass is equal to the mass number. The negative packing fraction value indicates that there is mass defect, hence binding energy, and such nuclei are stable. Whereas the positive packing fraction value means a tendency towards instability. However, this generalization is not correct for lighter nuclides. Now we can see from this plot that the nuclides having mass number 20 to 180, they have negative packing fraction values, so they are comparatively stable. And the least value has been observed for iron 56, so it is the most stable nuclide among the known nuclides. Carbon has a 0 packing fraction value because it is taken as a reference on atomic scale, and its isotopic mass is equal to the mass number. Helium 4 and oxygen 16, their packing fraction values are less as compared to their neighbors, so they are more stable. Now this table shows packing fraction values for different nuclides, and these calculations have been performed using carbon 12 as the standard for atomic masses. And as you can see that the highest value of packing fraction is obtained for hydrogen, that is around 78. And those nuclides which have negative packing fractions, they are stable, whereas nuclides like uranium, radium, they have positive packing fraction values, therefore they are unstable. However, the generalization that the nuclides with positive packing fraction values are not stable is not strictly correct for lighter nuclides. For example, helium has a positive fraction value, but still helium nucleus is stable. And this can be explained on the basis that the actual masses of protons and neutrons are slightly greater than unity. If actual masses of the nucleons are used, then the situation is somewhat different. We get a negative packing fraction value, which supports the stability of these nuclides. Now, nuclear forces. In nature, there are 4 fundamental forces which are operative: the gravitational force, the electromagnetic force, the weak nuclear force, and the strong nuclear force. These forces are mediated by gravitons, photons, bosons, and gluons respectively. The gravitational force is the weakest among these 4 forces, and the nuclear forces are the strongest forces. Now, as we all know that within a atomic nucleus there are protons and neutrons. The protons, they are positively charged, and the neutrons, they are neutral. Since the neutrons are neutral, so therefore there is no repulsive interaction between electrostatic repulsive interaction between these two particles. However, since protons are positively charged, therefore there exists an electrostatic force of repulsion between two protons. However, even in the presence of this type of electrostatic force of repulsion, the nuclei are stable. So definitely there is some sort of force which hold these protons and protons together, or the protons and neutrons together, or the neutrons and neutrons together. So this force of attraction is basically the nuclear force. Or in other words, I can say that the force which holds nucleons together in a nucleus, despite the presence of very strong electrostatic repulsion between the protons, is called the nuclear force. As we know that all forces arise from exchange of particles. For example, the electric force arises from the exchange of photons. So the nuclear force, it arises by the exchange of pions. At a more fundamental level, the strong interaction is responsible for the formation of protons and neutrons by binding the quarks through gluons. Then the residual energy is used to bind together the protons and neutrons to form a nucleus. This residual energy is called the nuclear force and is in turn mediated by the exchange particles, pions. Now, what is the range of nuclear forces? So, if we plot the strength of force versus the internucleon distance, we get a plot like this. This red line is showing the electrostatic force of repulsion, and as the nucleons, especially the proton, they come close to each other, then the force of repulsion increases. However, in case of nuclear forces, when the nucleons, they come close to each other and they are at a distance of about 2.5 femtometers, then this force starts operating and the attraction between the nucleons increases and reaches a maximum value about at a distance of around 1.2 femtometer. However, if the nucleons, they come close to each other, then after a distance of around 0.5 femtometer, the force of repulsion starts to appear between the nucleons. Now that's the reason that the protons and the neutrons, they retain their identity and the nucleus doesn't collapse on itself. So the nuclear force is a short range force and is effective between the nucleons at a distance of about 2.5 femtometers and becomes a repulsive force if the distance between the nucleons decreases from 0.5 femtometers. Now, some of the important properties of these nuclear forces are: number one, the nuclear forces does not depend upon the charge of nucleon. Number two, the nuclear forces acts over a very short range in the order of femtometers. Number three, the nuclear forces show the property of saturation. That is, it involves the immediate neighbors and not the other nucleons, as is evident from the almost constant binding energy per nucleon, that is 8 MeV of most of the nuclides. And number four, the nuclear force is a non-central force, and this means that the nucleus is not spherically symmetrical. Our next topic is meson theory of nuclear forces. This theory was proposed by a Japanese theoretical physicist, Hideki Yukawa, and he was the first Japanese Nobel Prize winner. According to Yukawa, the nucleons, they interact with each other through exchange particles, and he called these exchange particles as the mesons. According to him, the proton can interact with a neutron, and during this interaction a neutron is converted to proton with the emission of a negative pi meson, and this negative pi meson is then absorbed by another proton, and that proton is converted to a neutron. A proton can be converted to neutron by emitting a positive pi meson, and then this positive pi meson, it is absorbed by another neutron, and that neutron is converted to a proton. The neutron can also interact with neutron through neutral pi mesons. So during this type of interaction, a neutron is converted to another neutron with the emission of neutral pi meson, and that neutral pi meson is absorbed by another neutron, which is converted to another neutron. Similarly, a proton can interact with proton, and during this interaction a proton gives neutral pi mesons, and then these neutral pi mesons are absorbed by other protons. So these exchange particles, the negative pi mesons, the positive pi mesons, and the neutral pi mesons, are the mediators, and they are responsible for the existence of nuclear forces. Now summary. Packing fraction is the mass defect per nucleon and can be used to assess the stability of a nuclide. Nuclear forces are strong forces which operate within the nucleus and are primarily responsible for the stability of a nucleus. According to meson theory, nuclear forces are mediated by mesons. So this is a list of books which you can consult for further reading, and thank you.